Okay, this is part 4. The exam is Pearson Edexcel International A-Level for Physics, also known as IAL Unit 1. It's the exam from last summer, May 2024. It covers topics of mechanics and materials. So it's also very helpful to students studying for the linear exam because the topics are exactly the same and they will help you prepare for your end-of-year exams as well as prepare you for the technique used in all of these A-level papers. So the problem with the linear is you only get exams in June, whereas the international A-level has sittings in January, June and October. So you have 3 times the number of exams that you can use to practice with. And students who are the most successful are practicing as many past papers as they can find, and they're doing them more than once. So that's my recommendation: do as many past papers as you can, and successful students are the ones that work the hardest between the lessons. The lessons are just an introduction to the concepts. They will not allow you to reach the highest level that you need to get to the highest grades. Okay, so don't forget to like, share and subscribe as I'm scrolling through the sections we've already done. We've done up to question 15. Okay, so the first 15 questions are generally more straightforward, and as you go towards the latter half of the exam, 16, 17, 18 and 19 are left. They get gradually more difficult, and you want to get as many marks you can for the easier section, and the end of the exam sorts out the students in terms of the differentiating between them in terms of the higher grades. Okay, so we just finished a question on momentum, and here is a question on Young's modulus. So Young's modulus is in the materials section, which is both in the linear and the modular exam, and it's one of the core practicals that you need to know how to carry out. There are 2 methods. One of the methods is to stretch a wire along the length of a bench using a pulley, as shown in this diagram. The other is to use a more technical set of apparatus which you would need to hang from the ceiling in the lab, and they need to be set up a little bit more securely. Okay, so it depends which equipment your school has bought in terms of doing this experiment. So it says a student carried out an experiment to determine the Young modulus of copper. Okay, normally the 2 materials that are most commonly used are copper and steel. Okay, so the Young modulus for a material is a constant for the material. Okay, so it doesn't change according to its length or its dimensions. So it's just telling you. Now these questions, where they have an asterisk, means they're communication questions, whereas the qualitative answers that gets the marks rather than a mathematical proof. Okay, so it says a student clamped one end of a copper wire to the bench. Yes, so here at the clamp. Okay, and usually you put blocks of wood to hold it firmly in place, and the wire passed over a pulley. Yes, at the other end, where masses were added to extend the length. Okay, so a meter rule was fixed on the table. Yeah, so you fix the meter rule on the table so it's not moving, and you put a marker like a piece of tape on the wire, and you're measuring from that marker position. Okay, so you're seeing as you put more masses, it's going to pull the wire, and the marker on it will move along the meter rule, so it allows you to see how much the wire starting from the marker position has stretched. Okay, because obviously the force is stretching the whole length of wire, so you've got to analyze what's going on. So that's the basic setup. And now let's go into the question. The student measured the diameter of the wire. So obviously, how do you measure it? It's with a micrometer. Yeah, a micrometer has a resolution of 0.01 millimeters. So you can measure to 100th of a millimeter. You need to make sure your teacher has shown you how to use a micrometer. Okay. In the linear exam, the final paper of your A-level after 2 years is a 2.5-hour exam which includes the practical skills as well as the theory from any section of the A-level. Whereas in the international A-level paper, there is a practical exam at the end of year 12. It's called Unit 3, where they're concentrating on the experiments that they want you to have carried out, and they will ask you about resolution, uncertainties, and how you overcome them, okay? How you deal with them. So then the question is asking you to describe, yeah? So this is the active part of the question. So you've taken all the information in. So this is all about reading it, understanding what they're asking you, understanding the method. Make sure that you've done the practical and you have your methods written up in detail for all the core practicals. You need to know the method, how you analyze the results, and what are the normal pitfalls in the experiment, including risk assessments and hazards. It says describe the other measurements, yeah, other than the one which we talked about with the micrometer, that you need to make, that need to be made, it says, using the apparatus, and how they will be used to determine the Young modulus of copper. Okay, so what else do you need to measure? You should define the meanings of any symbols you use. So that's a good point to explain to students revising for their exam. Don't put symbols if you haven't defined what the symbol is. They don't know if you know what the symbols mean. Okay, so normally every symbol used must be defined. So the first thing you need to measure is the original length. The original length is from the clamp to the marker, because basically from here to here is the length of wire that you are stretching. Yeah, so that's the active part that you're stretching. So if the marker moves to the right, to the left in this diagram because of the masses, you've stretched that length of wire from here to here. So this is your original length, the red part that I've scribbled on the diagram. That's your original length. So you need to say, measure the original length from the clamp to the marker, okay? Before extra weights or masses are added, because remember the extra weights are what causes the extension every time you're adding it. So you could have one weight on there already as your control to make sure that the wire is nice and straight, okay? Another common problem with this measurement is if the wire has got any kinks in it. Kinks are little bends in the wire which could then straighten out as you put it under tension, and they're not actually extending the interior structure of the material. They're just ironing out the inaccuracies of the original length, okay? So you also need to think about that when you're doing this experiment. It's a common question that is often asked in A-level. You then measure the distance, so this the second thing you need to measure. The second thing you need to measure then is the distance moved by the marker, yeah, from the original position to determine any extension, obviously, when you add weight, yes? And of course you would need to calculate the weight because it's mass times gravity, and here you've got masses. So you've got to explain that that's 3 marks, that you need to calculate the weight using W equals mg. So that will be a kind of mark that a beginner student will not think of, the attention to detail. There are 3 things I teach my GCSE students which apply in A-level as well. You need to have detail, clarity, and depth of understanding to get all of these marks, okay? Then you use the diameter measured, yes, here you've measured the diameter using the micrometer to calculate the cross-sectional area of the wire. Why do you need that? Because you need that to work out the stress of the wire, okay? So you have to calculate the cross-sectional area. And then what you then need to do is to calculate the stress and the strain, okay? So you calculate the stress and the strain for each reading taken, yeah? It's because you've taken readings of weight and readings of the marker position moving, therefore the extension. Okay, so you want to change the weight, which is force, into stress, and the extension divided by the original length into strain. Because, as you know, to calculate Young's modulus is the ratio, yeah, of a stress to strain graph. So it's the gradient, I've missed the T off, the gradient of stress strain, yeah, the gradient of stress strain graph, the linear section. And that really covers the 6 main points for this 6-mark question, which is qualitative in style. So these questions, there's one at least in every exam paper. You've got to get used to the level of clarity and detail required. You need to know every core practical. Yeah, even if you haven't carried it out for the International A-level paper, you need to know all of the intricacies of the core practical exams. Okay? Once you have that, then in this question they're asking you to do some analysis. Okay? So it says another student attaches a weight of 5.0 newtons to a copper wire of diameter given 0.56 millimeters in diameter. Calculate the extension of the wire. So we know the force, we know the diameter, and we've been given the original length of the wire as 2.5 meters, and we know Young's modulus for copper is given to us as well. So we know everything except for extension. So they want you to use D to work out the cross-sectional area, because that's pi r squared, or you could just say pi d squared over 4 if you want to do it all in one step, and you will get the area first. You'll get a mark for working out the cross-sectional area, and then you can work out the stress as being the weight, which is 5 newtons, divided by the area you've calculated, which will give you the stress for your second mark. Once you've got that, you need to show that you know Young's modulus is equal to the stress to strain ratio. We know the stress is given to us in the calculation above. We don't know the strain, so we want to work out the strain. Yes, the strain is Young's modulus, or is the stress divided by Young's modulus. If you change the subject of the equation, you can then put it in, and you work out that the strain for that stress for copper would be 1.85 times 10 to the minus 4, and it has no units, and has to 3 significant figures. So once we know that, we also know that strain is extension over length, and this allows us to work out the extension as being the strain multiplied by the original length, which is given to us as 2.5 meters. So you multiply the strain at that stress by 2.5 meters, the original length, and you get a strain of 4.61 times 10 to the minus 4 meters to 3 significant figures, which you could then round up to 2 significant figures for the end of this 10-mark question. Okay, so that's a question on one of the core practicals. And you'll see that different core practicals come up in different exams. So you have to practice them all, and you won't know which ones will come up in the exam that you take. Okay. The next question is about projectiles. So we try to do this one in the same video. The child is playing a game. The child is trying to get stones to land inside an old tire floating on the water, and you can see that in the diagram. So they're given the initial, the child is standing, his hand where he's throwing it is launching the stones, is already 1.25 meters above the surface of the water. So you've already got an initial height, yeah? And the child throws a stone at a speed of 6.3 meters per second at the angle shown of 55 degrees to the horizontal. So you can resolve that initial speed, yeah, or velocity, 6.3 meters per second, into horizontal and vertical components, yeah, which you need to do for all projectile motion. The stone leaves the child at a height 1.25 meters above the surface of the water, as I've already described. Okay? So how do you tackle these problems? Yeah, well, you've got to use your trigonometry to be able to solve these problems, as well as your ability to resolve vectors into two components. So question A is asking, show that means prove mathematically the vertical component of the stone's initial velocity is about 5 meters a second, and the horizontal component is about 4 meters per second. So does UH come to 4 meters per second and UV come to about 5 meters per second? Well, I've done it here on the diagram. U vertical is 6.3 times sine of 55, because you're going away from the angle, and I always teach my students that's the quick way of remembering it. So the vertical velocity will be 6.3 sine 55, yeah, which comes to 5.16 meters per second, which is approximately 5 meters per second, as expected, to one significant figures. You then do it for horizontally. Well, if the vertical component is sine 55, the horizontal component must be cos 55, and that gives you an answer of 3.61 meters per second to three significant figures, which is equal to 4 meters per second to one significant figure. So we have shown that, and we've shown that, and we got the 2 marks. It's quite a lot of work for 2 marks, and this is a standard expectation for A-level students, to be able to resolve any vector into horizontal and vertical components, or at components which are at right angles to each other, because it doesn't always have to be horizontal and vertical. Part B then says, show that the greatest height above the surface of the water reached by the stone is about 3 meters. So now you've got to look, we're talking about vertical height. So you have to write down what you're given vertically. So I teach my students to write down on the right-hand side of the space that you're provided everything you know. Well, we know from the resolving bit that we did for part A above that the vertical velocity is 5.16 meters per second, and we don't use the rounded up values. We know the acceleration is slowing it down, so it's minus 9.81. We know the final velocity vertically will be 0. At its maximum height, it will reach a velocity of 0. And we want to find out what is this height, S. So what will be the height will be the distance vertically, SV. So at maximum height, we know the vertical velocity is 0. We can now use what we have here, which is V, U, A, and S. So you can use V squared equals U squared plus 2AS. The only unknown is S. So you can rearrange it, and S will be V squared minus U squared over 2A. Put the numbers in, you'll find this 1.36 meters from the launch point. And the launch point, remember, the boy was already, his hand was 1.25 meters above the surface of the water already. So you've got to add this 1.25 meters here. You've got to add that to the height that we just calculated, and that will give you a height of 2.61 meters to three significant figures, yeah, which is equal to 3 meters to one significant figures. So we have shown that it's about 3 meters above the surface of the water. Okay? Once you've done that, it then goes into part C. The inside of the tyre is 0.8 meters in diameter and is 3.9 meters from the side of the water. So the boy who's throwing it, the child who's throwing it, must throw it so its horizontal displacement that it travels horizontally must be between 3.9 and 4.7 meters for it to have a chance of landing in the space here. Yeah? So minimum distance he's got to throw is horizontally is 3.9, and it shouldn't throw more than 4.7 meters for it to land in the tyre. So deduce, it says, work out, yes, whether the stone thrown by the child lands inside the tyre. Well, we know that it's the height that it gains before it starts to come back down again was from the previous question. We worked out the height that it gets to its maximum height above the surface of the water, and then we got to work from there and see, well, how much more time will it be in the air for? Okay, so we've got to now work out how much time it's in the air for. So step one is always to determine the time of flight. Okay, so we know, again, we're working on the vertical motion. I'm just going to move the screen up a bit. We're going to work on the vertical motion, and this time we want to work out the time. Okay, so we know S was 1.36 meters for it to reach back down to this height. Yeah, so it's going to go up and then come back to that height and then fall another 1.25 meters. So there's almost 3 stages: going up, coming back down, so it's going to go like that, come back down, and then keep going down. So that's stage 3. Stage 1 is going up, stage 2 is coming back to the same height that it was launched at, and time 3 is to fall further. Okay, so it's 3 stages: going up, coming back down to the initial starting position or the starting elevation, and then stage 3, falling further. Okay, hope that makes sense. So given vertically that it will take a bit of time to reach the 1.36 meters above this dotted line. Yeah, so we can work out using T equals V minus U over A. Yeah, because you should know that equation comes from V equals U plus AT. Yeah, so you can put the figures in. You'll find that it will take 0.526 seconds for it to go up to the edge of stage 1. Yes, to the maximum height. Well, if it takes 526 seconds to go up, it takes another 0.526 seconds for it to come back to that same position. Okay, so you know something about the vertical height. Okay, now time taken to fall from the maximum height. Yeah, so it's going to fall 2.61 meters. So after it's gone up, it takes 0.526 seconds to go to the top, then to fall from in stage 2, the height that we worked out before, 1.36 plus another 1.25. It's going to take time to fall the maximum height, 2.61 meters. This time you can put in the equations S equals ut plus half at squared, where you know now from the end of stage 1 it's reached a vertical velocity of 0, so you can get rid of this bit and it's just going to be half at squared. That allows you to work out the time for it to fall stages 2 and 3. Yes, so you can work out the time in one go, and time squared, or time 2 squared, the time for it to fall, yes, will be equal to, so this is what we're doing now, we're doing time to fall, yeah, we know it now. We're going from the top, which is initial velocity is 0. We don't need the final velocity. We want to work out the time it takes to fall, because once we know the total time of flight, we can see how far it can travel horizontally, which will be the next part of the question. So we've got the time will be 0.73 seconds, because obviously it's going to be more than 0.526 seconds because it's going to fall further and it's already moving fast, so it will be slightly more than 0.526 seconds. So the total time of flight is going to add up those two times together. This one going up, this one falling down. You have a total time of 1.255 seconds, and I've put it to 4 significant figures, so we have the accuracy needed for determining whether the stone is going to reach the tire, okay, and not to overshoot it. So now we're looking at horizontal motion, and horizontal motion is much simpler because we can ignore air resistance. They haven't asked us, but in all of these questions, these are constant acceleration formulae, therefore we ignore air resistance for them to work. Horizontally, you always have the horizontal motion is the initial horizontal velocity, which we worked out in the component from the first part of this question, which was 3.61 meters per second. The time of flight is 1.255 seconds from here, and that will give you a distance of 4.53 meters, which is in the range between 3.9 and 4.7. So the stone will land in the tire because it's between the minimum distance 3.9 and 4.7 meters. So that is a long question to do with projectile motion. And that's a very good practice question for you to write up as part of your notes. So when you're doing these questions, the purpose of doing exam questions is to put together all the knowledge you've gained from the individual chapters that you studied, and to see how you need information from each chapter to be able to make model answers for solving real problems at A-level physics. Well, I hope you found it useful. Don't forget, like, share, and subscribe, and I will try and do the next section as soon as possible. Okay, so we've now gone all the way to the end of question 17. I believe there are only 2 more questions left for the next video. Hopefully we can do it in one final video. Okay, thanks for watching. Bye for now.